lá. Sério que esse lado? Assim? Tem certeza? Ah, tá bom. Technology is improving here in ICTP. We have now robots filming us.
Okay, so this is the first lecture by please.
Good afternoon, everybody. Boa tarde, buenos dias, ni hao. It's a pleasure to be here with you today. And I'm gonna, over this week, I will present a series of lectures giving a very broad overview of black hole astrophysics, or as I like to say, black hole gastrophysics, because here not only the space-time dynamics is important, but also the aspects of fluid dynamics and radiation and how these things interact with massive stuff around them is also important, besides the space-time dynamics and general relativity. So that's why I call it gastrophysics. I can talk a bit about gastronomy as well, but my gastronomical skills are quite limited. Let's see how this works. Yeah, it is working. And I'm coming from, I'm a professor at University of São Paulo, which is, if you take an Uber, it's about 30 minutes from here, 20 minutes, given optimal conditions, going up to infinity depending on traffic conditions, okay? To go from here to University of São Paulo. You're all very welcome to visit. More specifically, the Institute of Astronomy, Instituto de Astronomia, Geofísica e Ciências Atmosféricas of University of São Paulo. So let's begin by talking about the goal of my lectures. Can you hear me? Can you hear me? I don't think I even need this, but I think it's being recorded. Okay. So the goal of the lectures. Let's start with the 5 hours of lectures. As I said, I'm going to present a general overview of black hole astrophysics, and I will make it clear what I mean. And the focus here will be to understand the observational manifestation of black holes, particularly in electromagnetic waves, because plenty of the lecturers in the school treat carefully and in detail the space-time dynamics and gravitational wave radiation. And in my lecture, I will focus instead on mostly on the electromagnetic waves, the physical processes that couple black holes to electromagnetic waves, which is the first messenger that we use to study and understand black holes. Waves. And I will give a primer on the physics necessary to have an understanding of the systems, to have a broad understanding of black holes and radiation and their astrophysical manifestation. And so here is a disclaimer. Let's have a disclaimer here in red big letters. It will be impossible, of course, to cover all of the richness of black hole astrophysics in only 5 lectures in more or less 5 hours, okay? I will not pretend to cover everything. It's possible to do that. So instead, my here, sometimes I will talk a little bit about the details of the physics or the details of observations. But the priority here is that you leave this week big picture of the important role of black holes in astrophysics. Okay, so the focus here is that you have a big picture, and then if one or two of you or more decide black hole astrophysics, you can more or less choose where you go from here. Okay, so the big picture and the basic concepts. So this is an outline of the lectures, which I will more or less follow. So first I will give a very broad review of general relativity. I'm sure I heard that last week you saw hardcore calculations of space-time dynamics, different regimes of gravitational waves, probably event horizons. But anyway, it's always good to review important things, so I will probably repeat some of the things you already know. Hopefully I will repeat some of the things you already know, talking about general relativity, GR, and black holes. Then I will move on and discuss the ins and outs of black holes. Ins meaning accretion flows, how they interact with the surrounding matter that nature decides to throw towards event horizons. And the outs of black holes are the most powerful particle accelerators in the universe, and they also throw stuff away in outflows in the so-called relativistic jets. So I will give a very broad overview of the physics of this phenomena and also observations. Then I will talk about a couple of basic concepts necessary to understand the connection of this phenomena to radiation, because this is very important for astronomy. So I will talk a very broad brush picture of the radiation processes relevant to astronomy. Then phenomenology, meaning applications of these concepts to observations, and we have this ongoing quest lasting many, many decades of trying to make sense of the very complex zoo of black holes in astrophysics. It's very messy, but we are starting to put them together. And finally, I hope to talk about supermassive binary black hole systems in astrophysics. So this is the website. I mean, so this course, it has a website. You can, if you do it quickly, you can scan this QR code. I never tried scanning a QR code live during a talk, but maybe this works. Website is that one, and the slides will live there. I think they will also post the slides on the ICTP website, and also references, and also feel free to interrupt me anytime during the lecture. I'm sure you are interrupting the lecture a lot. I hope you are interrupting the lecturers a lot this school. So feel free to interrupt me whenever you want. And also email me, go after, let's talk, let's discuss science, let's discuss physics and astrophysics. So before proceeding, I wanted to start setting the stage for the relevance of black holes in the universe, the relevance of black holes in nature. And things started with general relativity and Einstein and the field equations, okay? But there was a real change of paradigm when astronomers realized that the even in the equations could actually exist in the universe. And this is always due to advances in the technology and instrumentation to make measurements to look at the universe. So there is a couple of historically important observations that really shaped the field and made us realize that black holes that nature actually cares about the black hole solution of Einstein's equation. I will develop of these observations in more detail in the next lectures. But the first observation probably we can trace back to the early 20th century, more specifically to 1918. And this was an observation by the American astronomer, I believe he's American, Curtis. I tried to find the paper, but unfortunately the paper is not available digitally. It's from 1918. It's a couple of 10 years before my grandmother was born. More or less 10 years, I think. And so Curtis, he in a report, an internal report of some observatories, he published an internal report where he was doing optical observations of the sky. And Curtis noticed something very curious, very funny in the optical observations of galaxies. Because we really didn't know that we live in we didn't really know that we lived in galaxies in 1918, right? This was shortly after 3 years after Schwarzschild found 3 years after Carl Schwarzschild found the spherically symmetric vacuum solution, the black hole solution. Okay, we didn't really know we were living in an expanding universe. Okay, so the scenario of physics and astronomy was very different back then. So Curtis was looking at the fogs, these clouds in the sky. He had some idea it might be what we now call galaxies. And he found using words, he found a curious straight ray in galaxy M87. Now we call it a galaxy. Connected with the nucleus by a thin line of matter. He didn't really know that it was matter, but he was making a hypothesis that it was a thin line of matter. What he saw was a lower resolution version of this image, okay? So Curtis, the white fog that you see in this image are many hundreds of billions of stars, okay? This is a galaxy, a giant elliptical galaxy that we call M87. And you can see the curious straight ray, right? The curious straight ray of matter. The center of the galaxy is there. Here is the galaxy, and here is the curious straight ray of matter flowing from the center of the galaxy down outwards. Okay. Actually, more or less, the physical extent of the baryons of the galaxy, they go up to here, more or less. So this curious straight ray of matter is actually going outside the galaxy. Something is powering, is accelerating, perhaps, matter with such an incredible power, this is not working, so something is launching particles with such strong powers that it has the speeds of particles are way above the escape speed of the ray. Yeah.
I'm asking a question. Maybe ray doesn't go to us, so light must be scattered to us. So there must be some values there scattered around to us.
There must be some light.
No, the ray doesn't come to us. It's pointing to direction. So what we see is basically the scattered light by the baryons of the galaxy.
No, we are not seeing scattered light. We are actually seeing a direct light from we now call this a jet, and we are seeing basically the synchrotron emission of the accelerated electrons in this curious ray of matter. Okay, so we are seeing the electrons like crazy in the magnetic field, producing synchrotron emission. Okay, mostly synchrotron, because this is an image with the Hubble Space Telescope. Okay, but Curtis saw a lower resolution version of this image 100 years ago. Yeah, and there is we think there is another side of the jet. It's symmetrical, but the other side we are not seeing because of relativity aberration effects. Okay, but I will talk more about jets. This is just. The second, we will talk more about jets as we move on. The second observation happened more or less 50 years after Curtis made the curious observation. So in 1962, this is a lovely story. So there was a team of people in the Baltimore area developing instrumentation for military satellites to try to observe nuclear explosions, okay, from the Russians. Okay, so this happened in US, okay? And none other than a gentleman, Riccardo Giacconi, was leading this initially military mission to observe X-ray sources. And at some point, I don't know why, they decided to point the X-ray telescope to the sky, and they started observing cosmic X-ray sources in the sky, okay? That we didn't even anticipate that there were cosmic X-ray sources in the sky, okay? And what Ricardo, not now our loved Ricardo Sturani, but this other Ricardo, he didn't know, but he was looking at the manifestation of what we nowadays call a black hole, okay? More specifically, a stellar mass black hole called Cygnus X1, that I will talk about this kind of black holes. 1 year later, a Dutch astronomer living in the United States by the name of Martin Schmidt, they were looking at some funny sources in the sky, some funny radio sources and some funny optical sources. And so Schmidt pointed an optical telescope to a very strong radio source called 3C273. That's the WhatsApp number of the source, if you want to send a message there. So he pointed an optical telescope to 3C273, and he found a very strong optical emission at the center of this galaxy 3C273, Martin Schmidt. And this is so fascinating and so nonlinear. And Schmidt thought that he was looking at a bright star in our galaxy. But then what Schmidt did is that he took a spectrum, he identified some emission lines, and then he was able to quantify the shifting of the lines with respect to lines observed in a laboratory, emitted by hydrogen, excited hydrogen atoms. And then he was able to derive the cosmological redshift of this funny-looking optical strong point source at the nucleus of 3C273, okay? And then he realized that this source is not in our galaxy, but more than 1 billion light years away from us. So look, if it is shining with the flux of a star, but it is 1 billion light years away, it means that it's more or less almost 1 billion times more powerful than a star. It has such a gigantic energetics, this system, that nobody back then really understood what could power such a strong phenomena, okay? So this was a paper published in Nature in 1960, and it inaugurated a new era of astronomy. He just discovered what we call now quasars. And he was a star, so he called a quasi-stellar object, quasar. But then we now know that they are not stars. They are interesting, the stars, no one cares. And finally, 4 years later, again, the synergies between military research and astronomy. Yes? We already knew about black holes, but believe me or not, black holes were very exotic in the 60s. So for instance, Roy Kerr went to a conference right after this, I believe it was right after this discovery. I don't remember when Kerr, I don't know how to pronounce the name, I don't remember when he published the Kerr solution. The 62? So what I read is that Kerr went to an astrophysics conference where they were discussing what was going on with these so-called quasars, and people really like, what is this guy talking about? He's talking about these things called black holes. They don't exist in astronomy. People didn't realize it was not in the mental landscape of people that black holes were actually existed. Black holes were considered a curiosity rather than something that could have a physical and the solutions that could have a physical meaning. Okay, so this is what I'm painting here, is the complex picture that led scientists to realize that black holes are actually can be useful to understand the universe. Okay, and these, in my opinion, are the four most important early observations that paved the road for a physical existence, for people to realizing that the black holes actually do exist. And finally, in 1967, again, the interesting relationships between military research. Again, a called the Vela satellites. They pointed at the sky and they found gamma ray flashes all over the sky. This was in 1967. They triangulated the signals from the 3 or 4 Vela, and they realized that the cosmic gamma ray flashes were not due to the start of the Third World War, but they were because there's something funny happening in the sky and producing very strong gamma ray flashes that we now call gamma. Until 1973, that's when they published the discovery of gamma ray bursts. Okay. So here is a picture of one early X-ray telescope, of the Einstein telescope, of 2 of these strong X-ray sources, Cygnus X1 and SS433. We will come back to them. They are stellar mass black holes in a binary system. This is an updated picture of a couple of quasars. So quasars are very powerful sources of electromagnetic radiation living at the centers of distant galaxies, and I will also go back to quasars. And of course, Schmidt couldn't really make such a beautiful images. They were taken with the exquisite spatial resolution of the Hubble Space Telescope. So what are the commonalities between these different observations that I mentioned? Okay. In my opinion, the first important thing is that whenever you open a new astronomical window, you will see things that people were not anticipating, okay, which was the case in the 60s, okay, and I'm sure that there will be interesting things with the new astronomical window of gravitational waves that we were not anticipating. And another thing is that as soon as they started having an idea of the luminosities, they were able to constrain the energetics of the systems. And they found a very serious energy budget issue, in the sense that the sources that they were observing, they seemed to be producing too much energy. Too much energy were being produced, and it's very hard to explain this source of energy without invoking relativistic phenomena, what I call creative energy sources. Creative in the 60s, now they are not creative anymore. So now I would like to talk a little bit about energy requirements for a quasar, okay? And what I do now, it's a very simple, it's almost a ridiculous calculation compared to the kinds of calculations that you have been doing so far with dynamic spacetimes and different regimes of gravitational waves. But just for us to have an idea of the crazy energy requirements for a quasar. More specifically, what I call the fuel requirements to power a quasar. Let me put the image of a quasar back here. So when you have a flux, okay, so the rate of detection, detection of photons on a detector on Earth, what we actually measure is that we measure a flux, okay, and we also measure. We have several different methods to measure the distance to cosmic sources, okay? For instance, measuring the cosmological redshift, and you immediately, by using the Hubble law, you can infer the distance to the source. And having the flux and the distance, you can immediately compute the luminosity of an astronomical source, which is, this is what you measure here on Earth. Okay, so this is the radiative energy diluted on an expanding wave front, centered on the quasar, in the center of the galaxy. So we divide by the surface area of the sphere, assuming isotropic emission. Very simple astronomy 101 calculation. Nothing mysterious here. You all saw, I think you all saw in your course, if you had some interest in astronomy. Okay, so you measure flux, you measure distance, and then you get the luminosity of the source. So we can write the luminosity like this. Follow me for a moment. Let's take the luminosity and let's use a kind of engineering here to try to understand what is powering this energy emission. What physically could be powering this luminosity here? Okay, so let's imagine. Okay, let's imagine that in our mind's eye that right now there is a black box. We don't really understand the physics of this black box. Okay. But you can put things in this box, okay? So this is what I call the fuel supply. And things are flowing out of this black box in an exhaust, okay? Which in this case is photons, but it could be other kinds of particles, it could be gravitons, photons, it could be neutrinos. But let's simplify things and consider the photons that we see in quasars, okay? And let's imagine here that we are providing as fuel, nature is powering the source with some inflow of matter, okay? Let's imagine that nature is powering this machine, this cosmic black box, because we don't really know what it's inside. With some inflow of matter, and then we can write very generally this very simple formula. There is no physics here so far. We can imagine that this black box is converting the mass energy associated with this, and I will call it m dot. So the mass energy associated with this inflow is m dot squared, okay? And let's not go very extreme levels, okay? Let's imagine that this black box is converting this rest mass energy with some efficiency eta, okay? So this is the crucial number here. The efficiency eta is the efficiency with which this black box will convert the available inflow into light, okay? And all the physics is here, okay? All the physics in this efficiency. If eta was equal to 100%, you will have the perfect machine converting the rest mass energy of this inflowing matter into radiation. But unfortunately, it's not very easy to attain astrophysical engines with such high efficiencies, okay? So, okay, this is observe. The physics is here, but I'm using an engineering point of view, and this is the fuel supply. Okay. So, taking what we know about astrophysics, we can make guesses to the amount of inflow that you need to power the quasar, the observed quasar emissions from the center of this gigantic distant galaxy, okay? So you can write this m dot as luminosity divided by the eta c square, of course. This, and then depending on the physics of the phenomena that you're interested in, you can make some educated guesses on the amount of inflow that you need to power whatever astrophysical phenomena you are observing, okay? So, 60s, the most powerful astrophysical engine, this is new, was the supernovas. The plural is supernovae. And supernova, they are releasing a part of the energy when nuclear fusion, okay? It's fusing hydrogen atoms into helium, or helium into carbon, or carbon into oxygen. And then when you look at the difference between the energies, the binding energies, there is a difference. So the difference is released in an exothermic reaction, a nuclear reaction, okay? And the efficiency of release of energy of supernovae, when we write this efficiency in this form, for a supernova, can you guess what is the efficiency of converting rest mass energy of atoms, of nuclei, into free energy in the nuclear fusion of supernova? Do you have any idea what could be this efficiency? Is it close to 100%? We could do a guess here. We could do a quiz here. 100%, 50%. Why not? 1%. Why not? Let's see. 10 to the minus 3. No, actually, it's better if I write it. Eta. Let's make here a quiz. Okay. Eta 1. 0.5, 10 to the minus 3, 10 to the minus 8. I'm curious to know, who thinks that the efficiency of astrophysical engines in supernova is close, not exactly 1, but very close to 1, converting the rest mass of nuclei into nuclear energy? Who thinks is 1? Can you raise? Nobody. Wow, okay. Okay. Was a student who like, oh, okay, so again, 3. No, okay. 10 to the minus 3. I will count. Okay, this is the winner. Well, 10 to the minus 8. 1, okay, good, brave. It's the actual professor. Okay, so this has more weight here. Let's put more weight. 1, 3, 4, 5. Okay. Well, the clear winner is this one. Oh, okay, guys. Unfortunately, you got it right. It's about 3 10 to the minus 3 10 to the minus 3, the efficiency of supernovae. Okay. So, if you take now and you plug in the actual observed, more or less average luminosity observed for a quasar of 10 to the more or less 10 to the 46, and now it's a blasphemy for physicists. We astronomers and astrophysicists, unfortunately, we use outdated units. We use CGS. Okay, this is the standard unit of measurement in astronomy, CGS. Okay, unfortunately, I hate it, but I cannot change the whole community. So 10 to the 46 ergs per second. Okay, so this is almost, I cannot remember the solar luminosity, the power released by the sun. Anybody has this number? 10 to the 30 something ergs per second? Or you can help me and use Google and find the solar luminosity. Solar luminosity, 10 to the 30 something ergs per second. Ricardo seems to be up on his game. Professor Sturani.
So I ask in watts, you have to convert to erg.
Can you help me? Can you help me out?
4 10 to the 26.
Ergs per second. Watt, okay.
So what is joule 2 seconds? Convert to erg is kilogram to gram, and meter to centimeter. So 10 to the 7.
10.
10 overall would be.
Make a guess here, and then you can check this. But I will make a guess that this will be 10 to the 10. 33. Is the solar luminosity. Okay, so this is 10 to the 13 solar luminosities, okay? So it is as if you concentrated, oh my God, what's the name of this number? Billion, 10 to the 9, trillion, 10 trillion suns in a region quasar occupies, which is less than 1 parsec, okay? Now we know that the region the quasar occupies is less than 1 parsec, so more or less than 1 cube. Okay, so you have to have 10 trillion suns emitting in a region more or less region within the nearest star. Okay, 10 trillion suns in this amount of energy in a quasar. So let's make an estimate here for this efficiency of a supernova, okay? For this observation of the luminosity, we can make an educated guess of the necessary fuel supply to the central engines of quasars, okay? So we go there, we take eta c square, we put 10 to the 46, we take here 3 times 10 to the minus 3, 3 times 10 to the power of 10 square, right? It is a messy number, which will be 927, 10 to the 20, 10 to the 17. Okay, let's give or take 46, 18, 28, 27. 27 grams per second. Do you agree? So you need to provide the central engine with 10 to the 27 grams per second, okay? And I remember this number, I remember that the one mass is 33 grams. That number I remember, though I might be wrong. But if I'm not mistaken, it's 10 to the 33 grams per second. So 10 to the 27, 10 to the 33. So, wait, 30. Okay, so this is over 1 second, right? So, quasars, they have lifetimes not of seconds, but of millions of years, okay? We now know that they have lifetimes of many millions of years, okay? So it is more interesting if we analyze the field requirements over extended periods of time, okay? So if we multiply now, if we convert this to grams, not per second, but grams per year, okay? So 1 year is more or less 10 to the 7 seconds, right? 10 to the 7 seconds in 1 year, okay? We will have the average requirements of the fuel supply of a quasar, which is 10 to the 34 grams over 1 year, 1 year is nothing in astronomy, okay? Nothing compared to the lifetimes of galaxies and lifetimes of quasars, okay? So you need to be providing, if we take into account that the solar mass is 10 to the 33 grams, we need to be providing to a quasar 10 fresh solar masses per year, okay? 10 fresh solar masses of fuel supply per year, okay? And inject this in a region with less than 1 parsec, okay? 1 parsec is 3 light years, okay? So it's more or less the size, the distance between the sun and the second nearest star, okay? Okay, so my point with this very simple calculation, there is nothing fancy here, there is no GR, really an engineering point of view on the energetics of a typical quasar, okay? But this is giving you an order of magnitude constraint on the physics of this object, okay? And let me tell you, it's not that easy to put 10 solar masses per year at the center of a galaxy with a size of less than 1 parsec, okay? It's not that easy. It's not impossible, but it's not very easy, okay? So this will set constraint. This is one of the things that was guiding the physicists back then on what could be powering quasars, okay? If it is supernova, then you need this, and this is not easy. It's not impossible, but it is not easy on a normal galaxy. We will come back to this estimate later in the lectures. Okay, just wanted to put this order of magnitude. So what happened over the years? The light switch is here, right? This is the one? Okay. So over the years, over painstaking discussions, there was one single picture that emerged to explain the different crazy energetic requirements from these observations. And this is the unified picture that emerged, okay? Of one accreting black hole. Accreting means that you have a black hole that is getting more matter inside its event horizon. There is something depositing matter, accreting matter onto the black hole, okay? And there is amount of free gravitational energy available in the surrounding space-time of this object that you can extract if you throw free particles in different types of orbits, okay? You can actually extract the gravitational energy outside the event horizon, and there is a lot of gravitational energy in the systems, okay? And this was the solution that converged. Different astrophysicists converged to this solution, explain several different types of observations, including the 4 observations that I described before. So there are a couple of elements here in this picture that it will be the subject of my forthcoming lectures. You have an accretion disk, which is the swirling matter around the event horizon. So because of conservation of angular momentum, you produce these disks, which is the lowest energy configuration of test particles around the central object. You have, of course, the event horizon, the surface of the membrane of no return. In many cases, you see this puzzling outflowing matter, that we call relativistic jets. I will talk more about this in my 3rd or 4th lecture this week, the physics of relativistic jets. So the ins and outs of black holes. Of course, you have the singularity, and you have something, well, I will mention later these 2 elements, the photon sphere and the innermost stable circular orbits. What physics do you need to make sense of this system? Well, to make sense of the physics of the accretion disk, the physics of the test particles, which are actually interacting in the system, okay? You need hydrodynamics, but actually this gas is highly magnetized, so you need to couple the equations of fluid dynamics with the Maxwell equations, and you have magnetohydrodynamics. If you want to describe certain kinds of phenomena out of equilibrium phenomena, you need to drop a thermodynamic description of the system and solve the kinetic theory, okay, which it is important in certain aspects. To describe the dynamics of the test particles and the dynamics of the horizon interacting with the test particles, you need, of course, general relativity. More specifically, we need the Kerr spacetime that we have known the physics of the Kerr metric for 50 years now. And usually in these applications, the Kerr metric will suffice us. We will not need to deal with dynamic spacetimes unless we are dealing with two black holes accreting matter and orbiting each other, which I will talk in my last lecture. And again, the jet is a very magnetized process, and we need, again, the magnetohydrodynamics, so-called MHD, to describe the jet. Okay, so these systems, they are very powerful electromagnetic radiators, and they are also very powerful particle accelerators. So the accretion disk produces a lot of electromagnetic radiation, and when I talk radiation here, I mean radio wavelengths, infrared wavelengths, optical, ultraviolet, X-rays, and gamma rays, all wavelengths we have access to. And the jet, we think that there are lots of proton-proton collisions happening in the jet. And so the jet accelerates cosmic rays and neutrinos, which is a byproduct of proton hadronic collisions in the jet. Okay? So for this reason, accreting black holes are of extreme importance to several different observatories in all these wavelengths. So here is a list of forthcoming major astronomical efforts in the community. Accreting black holes will be primary targets for the Giant Magellan Telescope, for the extremely large telescope. This is the American telescope. This is the European telescope. The Large Synoptic Survey Telescope, which will make a real-time movie of the entire sky, will be a factory of transient discoveries. Many of them, perhaps most of them, will be related to accreting black holes. Also, the Cherenkov Telescope Array, which is the next generation of gamma-ray telescopes, ground using the Cherenkov light technique, and also the SKA the radio antennas. Right now, accreting black holes are thought to be the major culprits behind observations in the Pierre Auger Cosmic Ray Observatory, which is located in Argentina. Are there any Argentinians here in the audience? Aha. Hola. Where is the Pierre Auger again? Which part of Argentina? I forget. Malargüe, right? Malargüe, yeah. And also the Ice Cube, not the rapper Ice Cube, okay? There is, as many of you might know, there is a neutrino observatory called Ice Cube, which made a major discovery published in 2 science papers last month, where they think they are seeing neutrinos emitted in the jets from accreting black holes. No. This was the diffuse emission was 3 years ago. The Blazer one was this year. But the analysis has been going on, of course. It was published a month ago, 2 months ago, yeah. Some people think that this result might give the Nobel Prize to Francis Halzen, which is the leader of the Ice Cube Observatory. Well, it is possible that we also have binary black hole systems where besides accreting matter, you have the dynamic spacetime, and in this case, it will also have strong perturbations of the metric and therefore ripples of curvature, ripples in the metric tensors, the gravitational waves, as we know. And so accreting black holes, we cannot ignore the electromagnetic radiation, as we know, and we cannot ignore as well in this case gravitational waves. So they are primary targets for LIGO in the case of stellar mass systems, and in the case of supermassive systems, they will be primary targets for the LISA space interferometer, which is essentially you take LIGO and you put it on space, more or less. Simple, but the broad picture, the broad brush picture is this. So the bottom line so far of the lecture is that It is sad that in the 60s we had the golden age of black hole physics, okay, with the discoveries of Kerr, Riker, Penrose, Hawking, the singularity theorems, Hawking radiation, no-hair theorem, the cosmic censorship conjecture. I believe that we entered a second golden age of black hole physics. The first one was driven by the brains of people, the brains of theorists. The second golden age of black hole physics is powered, and you can be a part of it. Okay, I think that's one of the points, perhaps, of this school is that you can be a part of it. If you want to go in electromagnetic, you can do it. Gravitational waves, you can do it. Okay. So now we'll move on to the primer on GR and black holes. Any questions? It's been very qualitative so far, right? Before I move on, I wanted to understand a bit of the audience here. So I wanted to make a quick quiz to try to understand what is your background, where are you coming from? All of you have internet connection. Do you have smartphones? Please take your smartphones, take your tablet, take your computer. You will need a device. If you have an AI implanted in your brains, connect your AI to the Wi-Fi right now. And I want you to take your connected device and you go to this address, kahoot.it. Go to that address, kahoot.it, and punch in this code, this PIN code, 987563. I think this will help me and probably will help Professor Huza there. There is a soundtrack as well. Professor Hus and Professor Sturani and Professor Yoko don't need to join. You can join if you want. It will be fun if you join, but you don't need to. Yeah? I cannot understand you. Huh? I can play Mariah Carey if you want. All I want from Christmas is you. 30 seconds. So the idea here is please answer honestly, and actually it doesn't matter your name right now. You can put anything as long as it's not a naughty nickname. It doesn't really matter. The point here is that I want to understand the kind of audience I have here, okay? That's the point of this survey. Okay, I will start in, okay, 5, 4, 3, 2, 1.9, 1.5. Okay, connected? Okay, 1 and, okay, 0. Please answer honestly the questions. Okay, very good. Okay, so we have a pretty flat distribution here. We have master students, we have PhDs, we have more or less the same numbers of undergraduate students, very nice undergraduate students. We have the same numbers of PhDs, masters, and also postdocs. Great, very interesting, good to know. So we have a broad level of backgrounds here. Next question. What is your research field? Choose the most appropriate option. Physics related to GR or gravitational waves? Astronomy or astrophysics? Other, penguins, biology? Physics unrelated to GR or gravitational waves? Let's see. Okay, so most of you are actually working on GR and gravitational. It's very important to know. Very important to know. I didn't know that. Some of you, 7, are doing astronomy. By astronomy, I mean, well, it's a subfield of physics, let's be honest, right? Astronomy. Astronomy and astrophysics. 4 are doing things unrelated to GR or gravitational waves, like Ising spins or quantum molecules. I don't know. I'm very curious what you're working. Okay, nobody's doing anything outside these 3 major labels. Okay, interesting. Where are you coming from? Were there any questions from this particular question here? Okay, so, very interesting. So most of you are not coming from Brazil. That's great. Really, really great. And, okay, so most of the attendants of the school are not coming from São Paulo, which is great. Very good. I mean, not that people from São Paulo are not nice, but I'm saying that it's a step towards broadening the impact of the school. Good to know, good to know. How good is your general relativity background? Choose the most appropriate. Sorry, I think that was a bit fast. Sorry. Okay, so most of you, okay. I don't know, did you notice the little emoji here on numerical relativity and gravitational waves? Okay, so most of you, if provided with the Einstein's equation, you will be able to solve it, derive the Schwarzschild solution. Most of you, given the Einstein's equation, will be able to derive a linearized regime of gravitational waves. And derive here, given 2 test particles with an initial distance of L0, you will be able to derive the effect of the passing of a gravitational wave with the 2 polarizations on this quantity here. That's what I mean. Okay, very good. Okay, very good. Good to know. So I will be able to go very quickly over the GR background. Have you studied fluid dynamics before? Fluid dynamics, what is that? No. I took an undergraduate course. I took a graduate course. Okay, so let's see. Half of you didn't really take a course. No, okay, let's one third. One third didn't take a course. 1/3 took an undergraduate course, and 6 of you took a graduate course. Okay, was this Newtonian fluid dynamics or relativistic fluid dynamics? We will find out. Very interesting. Okay. Have you studied the radiative transfer equation? Do you know what is the synchrotron emission? No to both? Yes to both. Yes to one of them. Okay, okay, so that's why we have a black hole gastrophysics course here. Very good, very good. Thank you very much for participating in this quiz. Now I understand better the audience. Perhaps you help also Professor Husa here. Surani, how much time do I have?
14 minutes.
14 minutes?
1-4.
Okay. Okay. So this was very helpful, guys, because now I can basically go very quickly on the GR background, because I think you should be teaching me GR here. So now let me put a timer here for, you said 14 minutes? I put it 30 minutes then. No, I'm kidding. 14 minutes, let's see, 13 minutes, good. Okay. So now the idea here is to make a broad review of basic general relativity and what are black holes, okay? What are reasons in physics? So as you know, if you want to write a concise description of quantum field theory, you need to write this Lagrangian, the Lagrangian of the standard model, with all the fields, all the couplings of the fields, things that I really don't understand. This is ugly, this is scary. But if there is a particle physicist here, you can convince me that this is not unelegant. However, the elegant part here is that you take the action from here and then you write this beautiful extremum principle, the Lagrange equations. For me, this is one of the most beautiful concepts of physics, okay, the most general concepts. And write the dynamic equations for these fields, okay? But look at this, look at the size of this thing, you know, look at this, why, right? When you go to general relativity, the gravity field, the graviton, of course, we don't have a theory for the graviton because we don't have quantum gravity. But classical GR, which is the GR we have, it's very simple conceptually speaking. The basic concept is the geometrization of physics. Gravity equals space-time curvature. And there is an equation teaching us what are the physical effects if you provide an initial energy mass pressure distribution. So this equation, which connects the distribution of mass and pressure in space-time, in space, with the curvature of space-time, is the Einstein's field equation, as you know, where you have different kinds of tensors which inform us of the effect of the stress energy on the metric, If you're not familiar, I think most of you are familiar with this equation, but you know, one side you have space-time curvature, the other side is a constant involving G and C times the matter energy pressure stress energy tensor. And of course, you have the familiar picture that you can create any sort of crazy mass energy distribution, and then if you solve this equation, it will inform you of the geometry of space-time around this distribution of energy. Interesting thing now is that if you can now understand what happens to test particles moving in this curved space-time. Okay, so we quantify geometry. The geometry that we would measure with ruler sticks is the line element with the, of course. The Newtonian analog of the Einstein field equation is the Poisson equation. And if you want to understand what happens with a test particle in a given space-time, all you need to do is, writing this variational principle for the action, you can derive the geodesic equation, Okay, there is a little bit of effort in going from here to the right side, but that's, you get the geodesic equation, which relates the acceleration, the far acceleration on the particle with the Christoffel symbol, which is this ugly thing, which contains derivatives of the metric tensor, and the four velocities of the particle. Parameterized in terms of the proper time of the particle, if you are dealing with particles that follow time-like world lines, and if you are dealing with particles that follow null world lines, photons, and other massless particles, then you replace the proper time by the affine parameter, because you want to choose the affine parameter because it leads to an easier solution of the problem. And that's it, okay? So this is the primer of a GR. And if you spend 1 year or 1 semester or more time studying this, you can do all sorts of fun things. And then you can do what this physics professor did in Mathematica. This is basically an embedding diagram. This is a representation of the embedding diagram of the curvature, a visual depiction of the curvature of space-time around some astrophysical object, the geodesic motion of this particle in this embedding, this practical embedding diagram. And then he gets very excited, and then he starts throwing things with orbits with higher, with varying angular momentum and varying energies for the geodesics that the particles follow in this practical embedding diagram. And here is a cool, I think it's one of the most beautiful practical embedding diagrams prepared for by the millionaire budgets of the documentary The Elegant Universe, of the embedding diagram of the curved space around the planet Earth, moving in a geodesic, in a time-like geodesic, in the space-time around the sun. I probably don't need to show this, but for those that don't have that they want to get very quickly the basics of general relativity, I suggest having a look at this paper. It's a very nice, concise tutorial on general relativity by Richard Price. It's very nice. It's in 6 or 7 pages. You see the essence of general relativity here. And of course, as you know, general relativity is a classical theory. Okay, there is no space for probabilities in GR. Okay. So in one sense, philosophically speaking, this is very cool, because if you are able to specify the initial conditions of particles, the answer will be there somehow. Okay, it's up to you, of course, to find a solution. And if you have complicated space-times, numerical solution is tricky. No wonder why it took many decades before, I think, Pretorius had the breakthrough of solving numerical relativity in a black hole merger, right? But it's a deterministic theory, as you know. So some of the things that we should not overlook here. Gravity is unscreened, okay? You cannot shield yourself from the curvature of space-time. Okay, so there are no negative gravitational charges. And for this reason, gravity is a long-range interaction. There is no characteristic length. Well, we can say there is a characteristic length in terms of the gravitational radius or the Schwarzschild radius. Characteristic length for the curvature of space-time. But besides that, there is no other characteristic length. And funny enough, gravity, as you know, is the weakest of fundamental interactions, okay, between elementary particles, which is one of the main puzzles of theoretical physics. But the thing that the combination of these three aspects, they explain why gravity plays such an important role in the universe. And gravity is the fundamental interaction that shapes the cosmological evolution of the universe. So another thing that it's good to remind ourselves is phenomena for which general relativity is important. And one very interesting global picture of the phenomena described. When is general relativity important? Okay, is that clear to you? I think it is, but let's remind, when is general relativity an important physical theory that you have? You cannot escape general relativity. Whenever the mass of your system, this laser pointer is not working, but whenever the mass of your system, whenever the ratio of the mass to the length scale of the system in the terms of this ratio goes to 1, GR is more important as you go close to 1. So this plot here is a plot of all characteristic masses of phenomena in the universe, from the quantum to the cosmological masses and characteristic distances. The quantum gravity is in the red part of this plot. Cosmology is on the yellow part. This line corresponds to the Schwarzschild radius, and inside the dark region corresponds to the interiors of event horizons. So we have several different phenomena here, a lot of phenomena, including DNA. We don't believe that GR is important for understanding DNA. Earth. For Earth, this ratio is 10 to the minus 9. This might not seem like a huge number, but GPS requires a precision of this order to have meaningful geolocalization of you using apps, okay? The sun has a factor of 1,000 larger, let's say, gravity. Okay, so GR is a first order correction to the Newtonian equations if you want to understand better the space-time of the sun. So this first order correction has very profound impacts. If you are a patient astronomer and you observe Mercury for 100 years, start noticing the first order effect of GR, which is the precession of the perihelion of Mercury. And also the being of space by the sun, which was a very complicated observation that the anniversary of this observation will be, I think, this month, I think. It will be celebrated all over the world. Huh? May next year. Thank you, Ricardo. Okay, neutron stars. Now we are talking. Neutron stars. You start going very close to 1. Okay, so neutron stars are profoundly relativistic phenomena. And finally, black holes. You go to very close to 1, and black holes don't make any sense without GR. Well, now I wanted to explain what is a black hole, but I think I can skip most of this. What is a black hole? Is it clear to you what is an event horizon? Yes, I think so, but judging by the answers you gave, I think so. What I was going to do, I was going to analyze the gravitational collapse from 2 points of view. From an observer desperate at the surface of a collapsing star, what the moving observer sees with a collapsing star, a pressureless collapsing star, versus an observer far away from the star. I was going to do that, but all of you, I think, know already about this. So very quickly, if the infalling observer is sending light rays to the observer far away, okay, you can characterize the characteristic scale of the curvature with the Schwarzschild radius. And the best way of visualizing what is a black hole is building light cones and seeing what happens with light cones. So these are the Eddington-Finkelstein coordinates, the Schwarzschild spacetime. This is related to the Eddington-Finkelstein time. And then you take an event and you launch light cones which depict the possible trajectories of light. And once I have a mathematical program that I wanted to open here, but I don't think it's necessary. Or do you want to see this mathematical program showing what happens? It's an interactive app I wrote where you drag the event and then you see what happens with the event horizon. I will not show it here, but what happens is that once you are inside a Schwarzschild radius, there is no other option for your light rays but to fall towards the physical singularity at r equals 0. However, if you are outside a Schwarzschild radius, your light rays of your desperate infalling observer, they can escape to infinity. Okay? My time is almost up, but the bottom line here is the black hole, the event horizon is a null-like surface which separates events which are forced to reach the physical singularity versus events which are still able to communicate with the exterior universe. So I think I will finish now my lecture. I will proceed tomorrow and start talking about the effect of black holes on their environments. Thank you very much. See you tomorrow. Everything was crystal clear. It was very easy so far, I think.
So it was a smooth start.
It was a smooth start. The hardcore calculations I heard from last week, it's good to just take it easy, at least for one lecture. Yep.
Well, I'm curious about how does it look like the event horizon when you have a rotating black hole?
Next lecture.
Okay.
No, repeat the question.
Okay, so the question is, I'm curious to see what event horizon of a rotating black hole looks like. And I will answer this question in the next lecture, the physics of curved black holes, the most important astrophysical black holes. Thank you for your question.
Because
Round.
I know that you have two horizons, something like that. Okay. So I know that you have two horizons, but
yeah, you have two
I don't know
horizons.
if you can go deep in that.
And you have a different singularity. Show tomorrow. If I ask your patience for tomorrow.
Okay, so we reconvene at 4:15. Am I right? Yes, 4:15 for second lecture by Jan.